Trig and Pre-Calc, welcome back. Today we're going to be talking about Extrema, continuing our discussion with the full function analysis from yesterday. We discussed domain and range and continuity yesterday in class. Today we're going to discuss Extrema, increasing and decreasing intervals, and boundedness. Okay, so Extrema. You've actually had experience with Extrema. You might not remember it, but you absolutely did. These are minimum and maximum points on the graph. So there are two different types of Extrema. You have absolute Extrema and you have local Extrema. So an absolute Extrema is Extrema that occur on the entire interval of x. So that means it is the absolute biggest or absolute smallest value that y will have across the entire graph. So for example, excuse me, let me get my pen set up here. You get to see how this little thing right here works. For example, this guy right here is going to be an absolute maximum. And that absolute maximum exists because it is the highest point. It is the maximum value that y can have across the entire graph. Not all graphs have an absolute max or an absolute min. This one happens to have an absolute maximum. So this has absolute maximum at, and these are points. Okay, so I underlined points up here for a reason. These are points, x comma y. This max exists at 2 comma 3. That is an absolute maximum. We do have things called local extrema, and that means that it's either a peak or a valley, but it's not the highest or lowest point on the graph. So for example, you can see the arrow pointing to the low point. It's a valley. It's where your pen is going to change direction. It is a minimum point locally speaking. It is not the lowest point of the entire graph. Okay, so this is going to be a local minimum, and this guy is at, again, we use, it's a point, 1 comma negative 2. It is not the lowest point of the graph altogether because our end behavior shows that it continues to go down in y value for all of infinity. So it doesn't actually have a minimum value. It has a min in that like neighborhood, if you will, but over the entirety of the whole graph, there is no absolute minimum. I also have a local max over here at negative 1 comma 2. It's a high point. It's not the highest. That's why it's a local maximum. So it's the highest point in that little neighborhood, but it's not the highest point in the entire picture, right? So absolute extrema, highest, or it could be lowest, absolute max, absolute min, and then we also have locals. Okay, here's where it's going to get a little interesting. In Algebra 2, we absolutely discuss increasing, decreasing, and it always is a point of confusion. But when we talk about increasing and decreasing functions, the increasing part talks about the y values. Okay, so y values increase from left to right. So if we look at end behaviors, if we're reading the graph from left to right, we are going up. Yes, it does turn and come down, but generally speaking, from left to right, we are going up. So this is an increasing function, right? There's a little bit of a squiggle in the middle, but if you zoom out and look at the whole graph, it's going up from left to right. Okay, so we got some decreasing action going here. So your y values decrease as x goes from left to right. Keep in mind, when I say from left to right, I'm looking at the x values going from negative to positive infinity. So x values from negative infinity to positive infinity. So this guy, if I go from left to right, it decreases. Yes, it comes back up in a little squiggly, but if you look at your end behavior, it is absolutely decreasing over the entire graph. Another way to look at this is if you connected the endpoints, you would have a negative slope, right? Like so, kind of the edges of your graph Going from left to right, it goes down. So that's decreasing. Conversely, in the first example, it goes up. So that would be increasing. And then our buddy over here, this little constant graph, it doesn't go up or down. It stays constant. So Y value. Y values are all the same for any X value or any input. Okay, so increasing, decreasing, constant. There's your increasing, decreasing stuff. So let's dive into it a little bit more. Over the entire graph of the ones that we see here, we are saying they are generally increasing. That's an increasing function. That is a decreasing function just over the large picture of the graph. But let's kind of dive into the pieces because, yes, they aren't all... We're not looking just at the ends, right? We want to look at the in-between and the up and down in there as well. So when you're stating what's increasing, decreasing, or constant, you're going to list the X intervals. And we do that because when we talk about increasing and decreasing and constant, that is referring to the Y values. Okay, so that there, when it says increasing, decreasing, or constant, this refers to the Y values. Wow, why is that? Okay, the Y values. So the X values, the X intervals, say from X is 4 to X is 7, my graph increases, right? So increasing from 4 to 7. Increasing represents the graph goes up. So using the graph below, we're going to talk about the intervals where X is increasing, decreasing, and constant. Okay, so increasing, we are always going from left to right. Okay, always, always, always. We're always going from left to right. Always. Think about a number line. Go left to right. Okay, so let's go. Let's talk about it. So going from left to right, my graph increases. So it's going to go, it goes up. Hopefully you can see that from left to right. Then it hits a maximum, and then it starts to go down. And then it hits a minimum, and it starts to go up again, and then it hits another peak. Think about a roller coaster. It hits another maximum, and then it goes down again. Okay, so let's discuss. For my increasing intervals, I am looking at this part of my graph, so that's the part that goes up. But what I want you to think about in terms of that is I want you to focus on this part of the x-axis. Up to this point right here, I'm going to put a little thing there, a little rounded bracket. This is all x values where my graph increases. Okay? And then I have from this point here to this part here, I have more of an increase in x values. Then for the y's, for decreasing, I'm going from this point to this point. My graph, my x values, from it looks like -1 to +1, my y values are going to decrease. And then from it looks like x equals 2, the whole way this way, my x values decrease. Okay, so let's write this out here. So increasing, I'm going to start with this guy right here. So my first interval of increase for my x values, I'm looking at -infinity to, that is going to be -1 for my x values. So remember, increasing discusses the behavior of the y values. So the y values are getting bigger from x is -infinity to x is -1. It stops there. It's not increasing at -1. It's constant at -1. We're just going to leave that be. Okay. And then it is also increasing my second piece over here. We're not typically going to include the 1s and 2s. I just want you to be able to understand where that's coming from. And then also from 1 to 2, my graph is increasing. Okay, so then we're going to look at decreasing. I apologize for the frog in my throat this morning. I don't know what's happened to me. So I have this section here is decreasing, and also this section over here is decreasing. Okay, so from -1 to +1, we have a section of our graph that's going down. We also have a second section of our graph from 2 the whole way to positive infinity. It's also decreasing. Okay, so here's my second little group of decreasing. That's how we write our increasing and decreasing intervals. Okay, again, we're always going to go left to right. You're always listing the x values in your intervals. The increasing piece discusses what happens with the y values. The y values are going up when x is between -infinity and -1, and also between 1 and 2. And our y values decrease when our x values are in between -1, +1, and also 2 and positive infinity. Okay. So let's take a look at another example. I want you to grab your calculator, and if you haven't already done so, I want you to clean out all of the equations in your y equals menu. Go the whole way down, make sure there's no random slashes or anything or symbols or anything in any of the y equals down below, because that will mess up your graph. I also want you to hit zoom and then choose option 6 for standard to kind of reset your graph. Anytime your graph gets like wonky and you're missing part of your graph, or it's like off-centered or something, or it's zoomed in or zoomed out, you can always hit zoom 6 to reset back to your standard viewing window where it's 10 in all directions. So you go from negative to positive, -10 to +10 on the x-axis, and -10 to +10 on the y-axis. So just go ahead and reset that real quick if you haven't done so. And then when you graph, you should see the picture that you see here. Because it's really difficult to explain on an iPad, and it's easier to watch a video, what I'm going to suggest that you do, if you don't already know how to do this, is watch a video that tells you how to find the zeros of a function using your graphing calculator. Okay, so I'm going to kind of put that in a little star up here. I'm going to quote it: find zeros using graphing calculator. Okay. If you don't know how to do this, I strongly suggest you watch a video. There are some videos in the folder from Sneeringer that's on our Schoology page. I have a video as well that I recommend that I will post on our Schoology page as well. So you can watch either one of those videos. You can look one up on your own. There's a million videos for this particular calculator that show you how to do it. But, excuse me, the reason it's important is because we need to know the exact, not the approximate, the exact value of that point right there, this guy. There is a point on that graph where my pen changes direction, where it goes from decreasing to increasing. I need to know what that point is. And that's going to be my boundary for my increasing, decreasing intervals. One way to do it, obviously, using your calculator. The other way to do it is knowing that that point right there is going to be, some value of x, 0. It is on the y-axis, or it's on the x-axis. So we know that the y value has to be 0. So using algebra, what we could do is we could say 0 is equal to 2x plus 3 squared. And we can figure out what x equals. So I would square root both sides, and I get 0 is equal to 2x plus 3, subtract 3 on both sides, divide by 2. So I get -3/2 there. So I know I can come on over here and get that out of there, and I can say this is actually -3/2, 0. So that is my that is my minimum. That is an absolute minimum. Absolute min at -3, 2. I'm sorry, -3 divided by 2, 0. Because that's the smallest the y value will ever be, right? That 0 Y equals 0 is the least value that y will have across the entire graph. Every y value is bigger than 0 because the graph only exists above the x-axis. The graph only exists above y values that equal 0. So that's our absolute min. And we can discuss, we're going to discuss the decreasing piece and the increasing piece. Okay, so from left to right, we have a decreasing portion, we have our absolute min, and then it increases. Okay, so for our decreasing interval, that would be from negative infinity to negative 3/2. Remember that the interval describes the x values. Decreasing talks about the y values. So the y values are decreasing when the x values are from negative infinity to negative 3/2. So that means that for our y values are decreasing between those x values. Okay. On the flip side, they are increasing from negative 3/2 to positive infinity. Okay. It's easier to use a picture to see this, obviously. There are ways to do it algebraically. I don't recommend them. Looking at the picture is definitely the way to go. Okay, so make sure you know how to use your graphing calculator. If you don't have one, this is really early in the year already, but if you don't have a graphing calculator, this is going to be almost impossible for you. So please make sure you have a graphing calculator used for your homework. Okay, last thing we're going to talk about is going to be boundedness. Boundedness, a function is bounded basically when there's like a force field that won't let your function go past a specific value. It's an asymptote, right? So it's like you have, it can be an asymptote, or it's just like in the last question where, you know, your graph doesn't go anywhere below y equals 0, right? I mean, and that is bounded below because it's like out of bounds. If you go over, it's not going to exist. So a function is found bounded below if there's a value b such that b is less than or equal to your function. So that means y equals b is going to be a lower bound. So in the example up above, it was bounded below. We're not really going to get into the specifics of the value that it's bounded by. I just want you to be able to identify if it's bounded above, below, or just bounded altogether. Okay, so if you look at a graph and it is very obvious that there is some kind of funkiness going on, that your graph doesn't go below a certain value, like the one you see here or the one in the last problem, that's called bounded below. Again, we'll get into more detail into like what those values are at some point. Okay, the next one, bounded above. So the image that you're seeing here would be a negative a value quadratic. So like the opposite of x squared plus 4 would be what this graph would look like. That's a very generic one, but similar to the last example, but a little bit different. This has clearly a bound above the graph. So there's something hanging out above the graph that won't let it go any higher, right? There's nothing that'll go above. So it is bounded above. A graph is just bounded, generally speaking, if there is, it's almost like an alley, right? I look at this one like it's like a bowling alley, right? So the bounds, the little dashed lines there create almost like gutters, and your graph only exists in between those values. So there's kind of a maximum and kind of a minimum, and your graph only exists in between those values. So it's just generally said to be bounded if there is a lower and also an upper bound. This is very much like this is a two-dimensional version of our one-dimensional boundedness that we talked about on a number line earlier in the year in our prerequisite chapter. So if you remember, we talked about if it goes to infinity, it's unbounded, but if it has circles, it's either closed or open or half open, and it's bounded. This is considered to be unbounded. And it is unbounded because specifically our end behavior. There is a piece of our graph that goes off to infinity. Okay, so all we need is one piece. Actually, I'm going to put one or more piece of our graph continues unbounded. God, why can't I can't write today. On to positive infinity or negative infinity, right? So this guy over here is going to go, oops. So over to the right, oh, well, let's start with the left, to the left. So our x values are going to go to negative infinity, right? This graph is going to keep going to the left forever and ever and ever and ever. And your function, your y values, your f of x values are going to go to positive infinity. We're going to talk more about that when we talk about end behavior here in the next few days. But end behavior is something that you discussed earlier, so enjoy the preview. On the other side of the graph, my x values are going to keep going to the right to positive infinity for all of eternity, and my f of x or my y values are going to go down to negative infinity. So we have some unbounded action going on somewhere. It could be either side or both sides, but it goes on forever in one direction. So that makes it considered to be unbounded. Okay, let's take a look at an example here. This is it. This is the last piece I'm going to talk to you about. And then tomorrow we'll get into symmetry. When we talk about boundedness again, here's our picture. Determine the bounds graphically or algebraically. Some of us are comfortable enough with being able to do this in our head, like 3x squared minus 4. I know that's a parabola. It's an x squared. It has a positive a value of 3. That means it opens up, which means it's definitely bounded below. That means there's a big portion of the graph below, or a big portion of my coordinate grid below the graph that's just empty. So this guy, I'm not asking you where it's bounded other than that it's bounded below. Okay, so there's like an invisible force field down here that's saying you may not pass. Thou shalt not pass. You cannot go below this point. So there's no y values that exist below a specific value. Okay, that's it for today. Thanks for tuning in. I appreciate your time and attention as always. Listen, I hope you have a fantastic day. I will see you tomorrow when we're going to talk more. Well, I'll review what we went over in the video, but tomorrow we're talking about symmetry, asymptotes, and end behavior. And that's going to wrap up this unit. This is a very short unit just about functions. And they're just analyzing what happens on a graph. That's it. Have a great day. I'll see y'all tomorrow.